Okay, might as well begin. Welcome. Any questions? What we have done so far? That's what I wanted others to be. Anyway, it's short. What we have done so far is looked at reactive species. What reactive species are? What's the need to study them? What's the significance of studying them, and so on and so forth. And then we looked at some concepts that are useful for manipulating reactive species. We need to apply some typical engineering concepts to easily manipulate reactive species. That's what we saw in the first chapter. After a lot of stories, introductions, and so on and so forth. Stories would be there throughout. Games will join us soon. And in these, after that, we looked at the principles, the basic principles that give us frameworks for analysis of reactive species reactions. One is thermodynamics, the other one is kinetics. Most of the principles we already already knew. We revised them mostly, and then we looked at how to apply them for analyzing reactive species reactions. Any questions, comments on any related aspect? All fine. Good. We are a month into the semester in chapter 3. It is, these are reasonably sized chapters. And there are only 4 basic chapters, after which we get into specifics, specifics related to our work, which are mostly on production using bioreactors and so on and so forth, how to improve them, and some cancer work and so on. Okay. Cancer came in the last decade. Yeah, I think we started it in 2011. It picked up in 2014 or so. The contributions came in 2019, things like that, 2018, 2019. So, so we have looked at various things. And that would become somewhat clear towards the end of the course also, our journey. And that's the basis for the book also, the research monograph with the initial chapters for teaching. That's what it is. Okay. So we are going to look at measurement of reactive species levels, which are important for us. Measurement, or at least estimation, is important for us, and number is important for us. That gives us some idea. We know that the number is not complete or may not be complete in some cases, but having a number makes a big difference. We kind of extend it to various things. We kind of extend it to ranking and so on and so forth, which I may not agree with, but as a principle in engineering, having numbers is certainly good. Okay. We tend to overuse it, I believe. But anyway, that's a different story altogether. Okay. Yeah. Do you know the story about impact factors, how they came into being? Journal impact factors. That's another number which I hate completely. Okay. I have no qualms in saying that, even at this time when that's ruling the roost. I've never paid attention to impact factors. I've paid attention to the prestige of the journal, yes. Many prestigious journals have high numbers, not all. So I go by the prestige of the journal. The last couple of decades, it has been difficult to convince others that the prestige is important, but I don't care. I'm done. So I've done whatever I could, and to the best of my abilities. Yeah, the story about impact factors. Impact factors came into being only in the early 2000s, okay, about 20 plus years ago, 22 years ago, maybe 20, 21 years, 23, 20, maybe 24 years ago. Okay. It was brought in by an organization in Philadelphia, which was called the Thompsons, isn't it? Some company. It started looking at citations in those various journals and started giving a number based on some normalization, and not much normalization was never done based on I think actual numbers. So in fields where there are a large number of people, the numbers would be larger. In fields there are like math, which have very less people, the numbers would be small. So those would be there. But they were brought in so that the librarians can make decisions on buying journals for their or getting journals for their libraries. It very clearly said, I mean, I've looked at these documents on the website because it was new at that time. So there is a ranking scheme that is given and all that, or at least a numbering scheme. There's no ranking initially. So we were all curious, so we went and looked at it before we formed our own thoughts about it. And that write-up very clearly said, pretty much in the middle, that these numbers are meant for this purpose. They are not meant to reflect the quality of the journal, nothing, blah, blah, blah. And using this must be done very carefully. It very clearly mentioned that. Okay. 6 months later, that thing was gone. It vanished from the website of that company because the numbers had become so popular. Administrators need numbers. I've been in administration, by the way. I've set up 2 departments, so I know how it works. But I've kept away from that view on things. Okay, administrators need numbers because it's much easy to justify things. Okay, they have a job to do, right? I've been in the state myself, so I know very well how difficult that job is. It's not easy if you want to do a good job. If you're on a power trip, then it's easy. Then it's easy. If you want to really do a good job, it's not easy. So having a number makes things easier. So whether a number really reflects whatever it is, and so on and so forth, really doesn't matter. Okay, that's how it came into being, by the way. And 6 months, that was gone. The basis on the people who formulated it was gone. It started getting used left, right, and center, whether it makes sense or not. Now it's all a mess, according to me. I don't know what's the way out of it. People have denounced it from time to time, very rightfully so, but that has not caught on very well so far. It caught on to a certain extent, but not very well. But I never care about these numbers. But I certainly care about the prestige of the journal. I need to publish them in good journals of repute. Reputation, not prestige. Reputation of the journal, yes. Scientific reputation of the journal. Okay. So that is till you guys came in and so on. We are into any questions, comments on the first 2 chapters? We completed 2 within a month, and we are going on to the 3rd one now. Any questions? Okay. Another thing, I've added some material onto your Moodle page. You might want to take a look at it. I've added them this morning. One is some resources, of course, which we'll discuss starting in today's class, and some exercises, some RS leverage exercises from the past couple of years. I started giving this exercise only about 3 years ago, I think. Started during the pandemic. So probably I have only 2 sets or 3 sets. From that, whatever little. The numbers have been around 14 students total, 14, 15 students total. So I guess there are only 3 reports, the ones that I liked amongst those. Don't be limited by them. They're just to give you an idea, and you do your best. And I don't think the possibilities are brought out very well in those 3. They did whatever they did. They did well for their work, but that is not comprehensive and so on. Okay, whatever can be done. I spent my last 27 years in manipulating reactive species. So that's the background with which I'm saying that you need to take that into account. Okay, so that is there. There is also some resources on my own resources on improving presentations and writing, scientific writing. I've done a lot of work on them. I have papers on them and so on. There's one paper there. You might want to take a look at that in your own time. I thought I'd open it up right now so that you can take a look at that whenever you want. As far as this course goes, I guess there are 3, right? I keep forgetting what I do. I keep changing it from time to time. Definitely these 2 exercises, leverage RS, a reasonably good high percentage, and then the critical review of at least 10 non-review papers. That is a big chunk. In addition, there are some incentive quizzes, open book incentive quizzes, to help you learn and make sure that you have read whatever is assigned. That will start coming up when we get into our work and so on. That I think is a small percentage, 10% or something like that. I think these are the 3 things that will go towards your grade, nothing else will go towards your grade. We'll keep playing, we'll keep having a lot of these tests and so on, so whatever, games, tests and so on. All those will not count towards your grade, all that are for learning. So that's the background information. Any questions, comments? So even the one exam that we had out of some compulsion in transport, we'll not have here. I'm very happy with that. Transport, I just cannot, I don't feel like getting out completely. Somebody might ask a question. Okay. Okay, now we get into measurement of reactive species levels. Again, the idea is not comprehensive coverage. It will be reasonably comprehensive, yes. Whenever there is a need, you go and read up. These methods keep on changing. There are better and better methods as we progress. So keep track of that if there is a need for you. Okay, but I'll tell you whatever is commonly used, especially in our lab, commonly used, and whatever background that goes with it. So then, okay, note this. I have been a little careful in saying RS levels. Okay, levels, keep that in mind. We'll come to that in a little bit. So measurement of RS levels or concentrations is an important requirement towards better understanding of the RS effects on cells from our approach point of view. Certainly, that's the way we approach all things. And recall that the RS reaction rates are really high, right? So the actual RS concentrations change rapidly in the intercellular space. Typical things. Some are slow, but usually they are fast. Therefore, there needs to be a clarity on the measured quantity. What are you measuring? What are you measuring it for? Right? Because any measurement has a finite time associated with it. That's always the case with biological systems. Whenever you take a sample, measure it, there is a finite time associated with it. You need to keep in mind that it exists. Whether your measurement is limited by that, you cannot do anything more. You're just trying to get some idea, fine, done many times, or whether you can correct for it and so on and so forth. You need to keep in mind when you do research on that. In this course, we are interested in measuring the pseudo steady state concentration of reactive species for most biological needs, okay, not the actual concentrations. Any questions, comments on those? So we are always comparing rates. We are interested in the slower process in comparison with the RS reactions when we measure them. Okay, when we measure the reactive species. So that must be firmly kept in mind. If that is not the case, then you need to take due precaution and change your things and so on and so forth. Okay. However, as we saw in the last class, in some last few classes, in some chemical reaction studies, say for determining the rate constant of the reaction, the need is measuring the actual volumetric concentrations of the reactive species inside the cells. Mostly inside the cells, right? So that could also be the case. We are not dealing with it. You need specialized, even this is specialized, but you need specialization, specialized things of a different kind, of the kinetic kind, to measure. We saw them, right? We saw pulse radiolysis and stop flow as 2 important methods for measurement. You're okay, or you need help, or is there a place? Can you ask him to switch off one of the ACs and sometime? Okay, fine. Or AC off panna mudiyuma. Madhav, if you want, you can shift to another place if you need the AC. Only that. This will be on. If you just move in front, that is good enough. Yes, turned it on. You'll get it from this, but good, very nice. Thanks. Yeah, it's that time of the year, I think so. So, you need to be clear about what you are measuring, especially with the reactive species. So, let us make a difference between concentration and specific level. So, our idea, I mean, our main aim is to measure the levels. So, species concentration, quite straightforward, species amount by the measurement volume. Okay, that is what the concentration is. It is always not, concentration is always normalized on a volumetric basis, except usually normalized on a volumetric basis. You could have surface concentrations also, where it is normalized on a surface basis. Cell concentration is nothing but cell mass per measurement volume, and therefore, the specific level of the species in the cell, specific level per unit cell, that is what we mean, is species amount by the cell mass. Okay. How do you get this from these two values that are measurable? You can typically measure concentrations more easily, right. So, these are the measured values: species concentration, cell concentration. Species, therefore, if you divide species concentration by the cell concentration, you would get the specific level of the species, or in other words, species amount by the cell mass can be obtained through the measured values of the species concentration and the cell concentration. Unless otherwise stated, we are talking about the specific level of reactive species, only that makes sense. Okay. If you have more reactive species per cell, the effects are going to be different, right. So, or in other words, your volume could be the same. There are, consider two situations: your volume is the same in your reactor or so, or in your shake flask reactor, whatever it is. In one, there are about 10 power 5 cells per ml, in the other there are about 10 power 7 cells per ml. You add the same concentration of, let us say, menadione or something like that, superoxide inducer. The amount of assuming it is well mixed, the amount of menadione that is available to this 10 power 5 is 2 orders of magnitude higher than the amount available to the 10 power 7 cells per ml. Okay. Per ml we are talking about. The total number of cells is going to be per ml into the total ml, per ml into total ml. Okay. All this interconversions you can make and convince yourself. But if you work in terms of concentration, this problem arises all the time. So, be very careful. Many of your recipes are in terms of concentrations, assay recipes are in terms of concentrations. So, make sure that your basis remains the same. Okay. Understand the recipe better, see whether it is giving you whatever you are trying to measure. Typically a big problem, okay, in the lab, and we go on for some time, then we realize, oh no, this is not give, especially new things. Once we have used it, we know what it is supposed to give. And it's very tricky. The measurements could be very tricky because they've been developed for a certain purpose, they've been using it for a certain purpose. We adapt it, we don't realize it, and so on, right? We, in the sense, others in the literature have adapted it, and then we adapt from them without realizing the errors. And sometimes it has been 3 months, 4 months before we realized our errors. Okay, so that's the way it goes. Be a little careful. Any questions? Now to the actual measurement methods. Our focus is going to be only on cultivated cells. You can measure in various different systems, you can measure whole body and so on and so forth. Our focus in this course is on cultivated cells alone. The reaction between the reactive species of interest and other compounds to yield products that are detectable through either fluorescence, absorbance, electrical measurements, typically through a probe, okay, which is sitting outside the cell or sometimes inside the cell also. These are the usual methods, or products that are made by this, which are separable by gas chromatography, high performance liquid chromatography, and so on and so forth, and subsequently you measure those products. That is also a method that is used for reactive species. Much less, we typically use fluorescence in our lab, heavily use fluorescence in our lab. So, this course will have a slant towards fluorescence. All these methods exist. That slant also reflects a slant in the literature and so on and so forth. The fluorescence methods are the ones that are most common. Okay. But all these methods exist. Depending on your need, you will have to choose your method. Okay. For example, I think did I talk about my PhD work in this course? intracellular pH? No. Fine. Okay. Or maybe you didn't get the context of it. So, I was in my PhD, I did work on mammalian cells, mammalian cells and yeast cells, and some bacteria also at times. No, bacteria, no. Bacteria came after I began my independent research. So, the the aim was mammalian cells, hybridoma cells. At that time, monoclonal antibodies were very big. Development of them were very big. I mean, development since the production, development of the production aspects were very big. So, hybridoma cells was what we were working with. The aim was to measure intercellular pH there, and working with them, working with mammalian cells is significantly more difficult than working with yeast cells. You don't have to do much for yeast cells in comparison, because you'll have to do a lot, but not much in comparison in terms of the care that you need to take, the effort that you need to put in, and so on. So, one of my group mates suggested, one of my seniors suggested, you can develop it in yeast and then move the same things to mammalian cells, which is a good idea, which my advisor also liked. So, I worked with developing it predominantly in yeast cells and then applied it to mammalian cells also. So, mammalian cells, looking at intracellular pH, right. There were dyes at that point in time which would change either their maxima, fluorescence maxima, or their intensity depending on the concentration inside the cells. Various different mechanisms. There could be self-quenching also, which is a mechanism that is used, which is decrease in fluorescence and so on and so forth. Let's not get into that. Fine. So, there are various methods. So, straightforward first thought was, there are these dyes, expensive, yes. There are these dyes. There was a dye at that point in time which had newly come into the market called BCECF-AM, which stands for bis carboxyethyl carboxyfluorescent, the acetomethyl ester form of that. Okay. So, you need the AM for it to be uncharged, for it to get into the cell, and then once it gets into the cell, it gets cleaved by the enzymes there, and then BCECF is the one that fluoresces. The fluorescence can be related to pH. Okay. Well known, rather it had come in new, but it was reasonably established by the time. So, the first thought was to try it out. My idea was to measure intracellular pH online continuously in a bioreactor, okay, using fluorescence method. We had a fluorescence probe which would measure, I had built a fluorescence probe, a spectrophlorimeter, right. So, we had a fiber optic bundle. One part of the bundle takes the light of a certain wavelength and irradiates it into the bioreactor, which through a fiber optic, this thick fiber optic probe that sits inside a well that sits on that is made onto the bioreactor. What is it called? Head space is the space here. The head plate. You have a bolt and then a well and then a quartz window at the bottom of it. So, there is no interaction between the probe and the culture. Sterility issues is a big problem. So, then we take this fiber optic probe, put this into this well, which is about this much, maybe about 2 centimeters, not even 2, 1 centimeter. And then, so the excitation wavelength goes in through one set of fiber optic probes, fibers, bundles, and then the emission which comes back from that is taken up and read. And it is typically these are 90 degree geometries. So, there is one that takes the excitation, the other angle reads it, typically in fluorescence. It is not usually direct. So, we had used that and we had designed a fiber optic probe to do all that. This is the way it was being measured. So, started measuring it. Things were fine for the first 2 hours. I was very happy. Then something weird started happening. I couldn't make sense of the data that was coming out. Then I realized after 2 hours, the dye starts leaking and the entire dye comes out in about 4 hours time. So, it's not useful after 2 hours. I need it for 48 hours, right. So, I cannot use that dye. for the purpose that it is meant. Okay, expensive dye for the purpose that is meant. So then go to library. At that point, only libraries, we had access to pen library, which is much bigger. Drexel library, pen library, and then search. Go back 20 years, and somebody had used um, weak base 9-aminoacridine to measure pH. What happens is it's a weak base, so the ionized form has the ionic form H plus and whatever form. So the weak base in its uncharged form gets into the cell, it gets cleaved, no, not cleaved, it establishes a new equilibrium inside. It's a weak base, right? So depending on the pH, it will establish a new equilibrium inside. And there is some quenching that happens there. So whatever fluorescence, whatever dye, is inside the cell will not contribute to the fluorescence. Whatever dye has been broken, has been dissociated outside, will contribute. Therefore, if you measure what is the outside pH and the fluorescence, you can back calculate the intercellular pH because you know the difference in the pH and so on and so forth. You can read the paper, it's one of my first papers. The entire thing is given in detail there. So I had to go to a method which was 30 years old at that time, right? Because my purpose is different. So it depends on your purpose, what you need to measure. Coming back to our reactive species, we heavily use fluorescence. When we started out in 96, we used something called electron paramagnetic resonance to measure the reactive species levels, reactive species concentrations, and thereby find out the levels. However, that it's still the gold standard, by the way. EPR is still the gold standard, but it's very difficult to interpret, especially when you have mixtures of reactive species. When you have superoxide, hydroxyl, and all mixed up together, which you typically have in a cell. Very difficult. To deconvolute them is not easy. Whereas if you have a single reactive species, that's the gold standard. Expensive method, but that's the gold standard. The instrument was about 3.5 crores in about more than a decade ago. Oh boy. I finished my safe head term in 2013. At that point in time, we got a new machine just coming in. I've never used that, by the way. Coming in, and that I did the paperwork. I needed to do the paperwork for that. That was 3.5 crores at that time. So that's the kind of, that's why we have safe. Okay. Any questions, comments? So that's what I mentioned. EPR, electron paramagnetic resonance, or electron spin resonance spectroscopy. EPR spectroscopy or ESR spectroscopy. We are going to use the terms interchangeably in this course. However, I will point out the difference between them. There's a subtle difference between them. I will point it out when we discuss the EPR technique. Okay. Although fluorescence, we use fluorescence heavily. We have used EPR earlier, and that still happens to be the gold standard for samples which contain only one reactive species. More importantly, only one free radical, not a reactive species. It has to be a free radical. So RS with unpaired electrons, that is free radicals, can be measured through EPR. I have it here. Okay. Any questions, comments?